Hello, Kamal. We're taking you through review on a research paper on rapid antibiotic incubation-free determination of tuberculosis during drug resistance using machine learning and Raman spectroscopy. From here, we pick a few words, like, for example, what's tuberculosis? Tuberculosis is an infectious disease which mainly affects the the lungs. We know machine learning. Machine learning is the way of solving problems using AI and models. And then Raman spectroscopy itself is the study of absorption and emission of light and other radiation by matter. So Raman spectroscopy is a technique typically used to determine vibrational modes of molecules, although rotational and other low frequency modes of systems may also be observed. So we're going to be observing these molecules, these tuberculosis molecules, so that we can use them to make a model which determines them. So our introduction is, so tuberculosis is preventable. It's infectious, but preventable and curable. It's among the world's deadliest infectious diseases. Uh, this in part due the emergence of drug-resistant tuberculosis. Like before in the 1980s, when tuberculosis was a problem, they brought about drugs. And then after some time, antibiotics, I mean, and then after some time, these particular uh, particular pathogens who became a problem because they were becoming resistant to drugs, the antibiotics themselves. So, uh, our particular here, we're going to develop an antibiotic test for tuberculosis by combining Raman's spectroscopy and machine learning. So the problem statement is a very significance because it addresses a critical need for faster, more accurate TB diagnosis and treatment, particularly for drug-resistant strains, those ones which are resistant to drugs. And then this is going to be a better way of determining because before it was addressing getting to know that this particular strain is drug resistant. It often takes 40 days. So this is a better and faster way. So yeah, we're going to do this through innovative technology that's made both affordable and portable, making it suitable for widespread use. Then the research objectives are develop a rapid drug, such a rapid test, then which is fast and accurate for determining the drug resistant of Mycobacterium tuberculosis. Then reduce diagnostic time, address the lengthy diagnostic process of traditional methods, which take nearly 40 days. Enhance accessibility, develop a low-cost portable Raman microscope to enable point-of-care testing in resource limited settings, support global health initiatives, uh, and yeah, for the methodology, right here, we see that what we're talking about, that we're going to use light uh, to get to see the bacteria. Like we're going to use diffraction, uh, an incident laser collecting a spectrum from a single bacteria cell. So this particular bacteria cell is one, but we're going to be collecting the spectrum from this particular cell. Then the spectrum that we've written, or the spectra, are used for inputting a neural, for creating a neural network to perform a classification task that outputs probability scores for each bacterial strain. And yeah, this particular network, these spectra are used to make a neural network. And then this neural network, we're going to build a model which is going to output a class prediction. Is the particular uh, is this particular bacteria susceptible of strain of being a strain, and is it going to resist? So right here we have the concentrations for the 5 distinct strains tested across the 4 main antibiotics uh, using standard twofold dilution. This right here. And then these are the pictures. This particular from D to H, we are seeing the microscopic image of monolayer of resistant itself. There is amikacin. Amikacin is an antibiotic. All these are antibiotics. So the methodology we're going to prepare, how I talked about it before in the image above. That's yes, we're going to collect samples for TB positive patients, and then using Raman spectroscopy, we're going to cause this. We're going to collect the spectra using diffraction, and then collect Raman spectral data from a large number. Then machine learning integration, we're going to develop a populational neural network. And then we're going to develop and train a machine learning algorithm to analyze the Raman spectral data. These techniques are supervised learning. And then we're going to validate that data and see how accurate and reliable the machine learning model is, then develop a portable device, the Raman microscope that can be used in limited settings. Then we deploy. Then we're going to be being given feedback so as to improve. So data collection, we're getting collection from clinical samples. Then we're getting laboratory cultures. We create some on our own. Then the sample preparation, the Raman spectroscopy. The Raman spectroscopy. This was the data collection. We get the samples. After getting the samples, even the laboratory ones, we prepare them and then get the spectra of this particular bacteria. And then the collected data includes a wide range of samples. Then rigorous quality control measures are implemented. Then all collected data is systematically stored and managed. It's organized in databases with appropriate metadata, date of collection, resistance profile, and any other relevant information. So the results and discussion, we get to see the accuracy of the Raman spectroscopy created. The model itself had a high accuracy of 89 in identifying the antibiotic resistance profiles of mycobacterium, which causes tuberculosis. Then the speed of diagnosis, this method significantly reduces the time, unlike the traditional for traditional culture-based methods. It's also cost-effective because it's priced at less than $5,000. Then field testing in real-world clinical scenario settings, the portable successfully identified drug-resistant TB strains from sputum samples. Then the discussion, implications of the TB treatment, the rapid and accurate identification and significantly improve patient outcomes by enabling more precise and timely treatment. It has obviously advantages over the traditional methods, which is especially the time, and potential for wide application. Beyond TB, the methodology they developed could be adapted for other infectious diseases. The combination of Raman spectroscopy and machine learning has a potential to revolutionize diagnostic practices. Then challenges and limitations, there are a few challenges and limitations I'm going to talk about here. Then the future directions, which I also talk about. So the conclusions, we have rapid and accurate diagnostics, feasibility for resource limited settings, enhanced patient outcomes, broad applicability, you can use them almost everywhere. Then support for general health initiatives. So the limitations and recommendations, we have sample quality and preparation. We just used a sample data. Then we are generalizing for all. There's model generalization. The machine learning model is contingent to diversity and quality of the training data, the cost and accessibility. Further reductions in cost and improvements are necessary to ensure widespread adoption. the environmental factors, whereby the device's durability and reliability under varying conditions is crucial for its practical use. Continuous updating of models, and then the recommendations, we have enhanced sample preparation protocols, expanding the data set itself, then cost reduction strategies, improving the device robustness, ongoing model maintenance, and field trials and feedback, more field trials and feedback. As you can see here, as I come to the conclusion of my presentation, these are the acknowledgements that the particular people, or the particular people who developed the research paper had, and some included where they got the funding from. Yeah, and they acknowledged other people who had done the same kind of research. Anyway, thank you very much for watching the video.